Yes, okay. Yeah, okay, we start again. Introduction. These people are here from University, from Budapest. What's the real name? I think Budapest University of Technology and Economics. And they are here to give us a talk about vSwitch and caching and some shortcomings of the caching architecture that can cause a denial of service attack on the host CPUs. So, Levente.
So hi everyone, hi again, my name is Levente Csikor and I'm here with my colleague Gábor Rétvári from Budapest University of Technology and Economics. This is a joint work with Stefan Schmid from University of Vienna, Dimitrios, Pezaros from University of Glasgow, and Esteve, Rothenberg from University of Campinas. And we gave a title for this presentation like Smashing the Fast Pass for OpenVSwitch for Fun and Profit. And before getting into the details, I also have an about us slide, who we are, to give you some more insight. So I'm a research associate at the university, and Gábor is, wow, it's really strange, but he's a senior research fellow at the same university. We're working closely together, and the lab that we are affiliated with is called High Speed Networks Laboratory. And we have a strong industrial connection with Ericsson, where everything which is around the network data plane programming is in the picture. And we are working really closely together with them. So we have several joint publications, patents, prototypes, European projects and stuff like that. But even if we are really tightly coupled, we are always open for collaboration, joint work or whatever. So we can talk about any opportunities later on. So let's talk about the main part. So first of all, when OpenVSwitch was developed like a couple of years ago, it really wants to just meet the needs of the networking community, all the open source networking community. The main aim was just to provide a feature-rich OpenFlow switch, which can manage all the underlying networks below the KVMBs, the virtual machines. And due to its continuous evolution, OpenVSwitch became the de facto standard of OpenFlow software switch, and it also became the most popular backend in current OpenStack deployments. And it also started to gain a foothold in serverless environments as well. And of course, there should be a reason why OpenVSwitch is so famous. So the main reason was that it was always capable to catch up with, I would say, industrial needs, which is kind of close to carrier-grade networking. So it was really fast and even faster and faster without sacrificing its main advantages, which is the high programmability and the generality. So fast, but how fast the OpenVSwitch is? So basically, there are slow pass and fast pass separation in OpenVSwitch, which means that we have a flow table, which is on the top. A flow table actually contains an ordered set of wildcard rules. What the wildcard rule means that we don't need to exactly or explicitly specify how we are matching the packets. So like this, we can specify prefixes or even just a whole wildcarding the whole header field. It is also operating on a set of header fields, so we have like 42 or even more. It depends on which version of OpenFlow are we using. And we also have a set of packet processing primitives. So this is how the slow pass actually looks like, and this is managed by the user space application called the OVS vSwitch daemon. And of course, in this flow table, the flow rules can overlap. As you can see, the first rule is actually a part of the rule in the bottom. In order to fasten the packet classification itself, OpenVSwitch introduced this fast pass and slow pass separation, which means that when the first packet is coming in, it of course is subjected to full-blown packet processing. So when it comes in, it is needed to be sent upwards to the flow table to find the corresponding matching entry. But once it's happened, it's actually going to be cached in the OpenVSwitch kernel module, and all the subsequent packets of the same flow will be avoiding this slow pass link to the top. So this is how it can be fast. So only the first packet is subjected to this slow pass, and everything else is going to be in the fast pass. If you go further, these flow caches can also be separated into two other caches, and now, as Richard told in the beginning, so now we are going to focus on the caching architecture with OpenVSwitch. So OpenVSwitch got an exact match cache. It's a microflow cache. It's a paired transport cache, which caches everything which that the packet has, so all the header information. And we have a megaflow cache, which introduced a bitwise wildcarding in the caching architecture itself. So it's a bit more loose compared to the microflow. And this was actually the biggest performance improvement in OpenVSwitch so far. So let's see how it works. So when a packet comes in with these following details, there are nothing in the exact cache, in the exact match cache. So it will be sent up whether to check whether in the megaflow cache entry, in the megaflow cache table we have an entry for this packet. But of course, in the very beginning there is nothing. So then the packet will be sent upwards to the slow path, as we saw from the previous slide, and then a matching entry will be found. So it's going to be mentioned as because the IP source address is in the 10/8 prefix, and then accordingly the packet will be sent towards the other direction, and all the details will be cached. As you can see, some bits are masked out in the megaflow cache, so only the IP source address is there, but it also has a prefix, and everything else is, which is completely unrelated to the flow table, is masked out. However, in the exact match cache, you can see that everything is which the packet has is cached there. It doesn't really look like in reality like this because it is hashed, but it's just for there's just a hash, but this is more easier to show how it works. So now when another packet comes from another source, but from the same source IP address, we can see that there won't be any entry in the exact match cache because it is matching on the 10.0.0.1. So it's going to be sent upwards to the megaflow cache where there is going to be an entry for it. So this packet is also processed in the fast path, but now we exploited the megaflow cache itself. And when a third packet comes from a completely different domain, then of course there won't be any match on the exact cache, and of course there's also not going to be any match in the megaflow cache as well. So it needs to be again sent upwards to the slow path, where the matching entry will be found, and then as it was in the beginning, it's going to be cached as well, similarly to the other the previous cases. So this is how it kind of look like. So what does it do? So let's it's got a data structure itself, the megaflow cache. So now we're completely focusing on megaflow cache itself. So the data structure is based on the tuple space search, which is actually means that if there are entries matching on the same header fields, they're collected into some hash, and all the packets that are masked out can be found fast in these hashes. And to reduce the complexity, the slow path which is on the top, makes the megaflow cache entries non-overlapping. So actually the tuple space search algorithm, even if the entries wouldn't be, even if they were overlapping, it's already really a complex problem. But even if we make it non-overlapping, it's still really complex, but it reduces the complexity. So and when a packet is subjected to this megaflow cache, it will be all these masks will be actually so it's going to be searched sequentially. So if we have many masks, it should be searched sequentially. So that could be a cost-linear search if we have a lot of masks. I will show some examples to make it much clearer. So just assume that we got a hypothetical 3-bit protocol. It's going to be an access control list example. So this is the flow table. So we're matching on 0, 0, 0. There's going to be a load, and everything else should be dropped. So the megaflow cache actually needs to distinguish all the packets that could be coming in. So what does the megaflow cache do? Is if we have a flow rule on that part, which is on the top of the flow table, we need to specify an exact match on the L rule, because there should be a packet which has this hypothetical protocol 0, 0, 0, and I can allow it to my system, but of course everything else should be dropped. So there can't be any bits that are maxed out, because I really need to distinguish between what packets are allowed and what packets are not. But of course, we need to cover the rest of the problem field. I mean, problem field, so the 3-bit protocol field, to make it efficient. So if we would have exact matches on all the 3 bits, like putting a circle here, circle here, circle here, and all the 8 corners, that wouldn't be effective because it would result the exact match cache, of course. So why would I just introduce the same caching mechanism twice? So it tries to wildcard some bits. So let's see how can we cover this protocol field. So we can have a megaflow cache entry covering the bottom right edge as well. And as you can see that in the megaflow cache, now we messed up this bit. So it is actually masking out these 2 bits on the second position. And that we can also have an entry for that part. Now it's an exact match entry because there are no other solution to cover that. And of course, we need to cover the top of the cube as well. And you can see now that basically to cover all the possible protocols in this 3-bit range, we needed to have 5 entry in the megaflow cache to cover the whole space. And also note again that these megaflow cache entries, you cannot see it, but I can. So these megaflow cache entries are non-overlapping. So there are no packets that are matching more than 1 entry in the megaflow cache. So it's really important. And of course, there are other solutions. So it's not just one solution. I can also have this circle like here and having an exact match rule on that part. And what OpenVSwitch tries to do is that OpenVSwitch tries to wildcard most of the bits. So what OpenVSwitch does is something like this in this hypothetical example. So it will realize after some time that the whole top slice of the box can be covered by 1 entry, and now it reduced the number of entries from 5 to 4. So this is how OpenVSwitch tries to optimize for the number of megaflow cache entries. So we got a CORM for this. So if we have an ACL on W bit header field and then just a simple flow table with an exact match error rule and the default denial policy, there couldn't be actually any representation, which is better than ordo k time complexity with ordo k times 2 on the power of W, also on the power of W/k space complexity, which actually means that we have this free parameter k, which tries to balance between the time and space complexity. So if I put, so if k equals to 1, then it's going to be a really fast hashing data structure with a really big space in the memory. And I can also go for k equals to W when I go for the space limitation and I don't really care about the time complexity. And it turned out that OpenVSwitch tends to lean towards this k equals to W equation. And you can find this information in actually OpenVSwitch source code. So they put a lot of comments on classifier.h where they try to indicate this, that using these 0 bits and masking out bits is really, it's a really good thing, and it really fastens everything. But as you can see, they actually wrote into the source code that we don't know a good way to generate wildcard mask with a maximum correct number of 0 bits. So we use various approximations. So they don't really know what's happening during the packet processing. So let's see how this megaflow cache can grow. So we saw that even one simple flow rule on 3 bits can spawn actually 3 masks and 4 entries in total. At the end, we saw that when OpenVSwitch came in and optimized for the coverage, then we had 4 entries and 3 masks in total. So let's see how it would work for an 8-bit prefix. So like this is a 10.0.0.0/8. So this is the only error rule we have, and we have a catch-all rule on the bottom. And if we just go for these 8 bits, then if we generate the good packets or the proper packets to this flow table, we will actually end up having 9 megaflow cache entries and 8 masks in this system. So we can conclude that actually if we are on some specific header field, which is if it's got a bit width of 8, then we will have 8 different masks at the end, and probably with 1 additional entry. So you cannot see again here the bottom line, but these are the IP addresses that are actually covering in the megaflow cache. That's the exact match rule for the first rule, and this is everything else, like 128.0.0.0/8, and it's going down, and then it will have these 8 masks and 9 entries at the end. So let's see how we can actually exploit this if we are an attacker. So what can happen if some interesting packet sequence is coming into the system? So we have the same flow table here, like 10.0.0.0/8, which is allowed, and everything else should be dropped. Then if we have a packet generator as a gift for Christmas, then if we know the flow table, and if we know all the details that I just mentioned a couple of slides before, so if we know how the megaflow cache entry and the megaflow cache itself is built up, then we can deduct what are the packets that need to be sent to the OpenVSwitch itself to generate that amount of megaflow cache entries that we saw before. So these are the flow rule, these are the packets. So as we saw before, we need to have the 10, the 128, 40, 64, and so on. And if we send these traffic into the OpenVSwitch, we can actually enforce OpenVSwitch to generate that amount of megaflow cache entries in its megaflow cache. So we needed actually 9 packets to generate all the 9 entries in the OpenVSwitch. So let's do the math. So let's see how the megaflow cache can be grown. So for 32 bits IP source addresses, we can have 32 masks and 33 entries. And that's only one flow rule and one header. So it's really simple. No one uses that simple ACL at all. And we need to note actually that matching on multiple header fields, it will result in a cross-product problem, which means an exponential growth in the megaflow cache. So if we have a matching rule on the TCP destination port, and we also have a matching rule on IP source address, then the mask that we can have if we are generating the proper packet sequence can actually, I wouldn't say skyrocket, but it would skyrocket to like 512. And if you also introduce a third rule, which is matching on the TCP source port, for instance, then we will have 8,000 or even more masks. So now, if all the networking is working on my machine, I will show you a demonstration how it will look like about the dissemination. So we already contacted the OpenVSwitch developer teams about our finding. And as I mentioned in the beginning, it was a SICOM demonstration presented this year in Budapest. And of course, we have a more comprehensive work, which is about how to attack a public cloud data plane, but that work is still under review at the moment. So this is how the architecture will look like. So we have a KVM-based architecture, it's a synthetic setup. We have 2 server nodes, each hosting some virtual machines. And we have a victim. Now we call it victims. So the victim has virtual machines on both machines, and also the attacker has virtual machines on both servers. And they are connected with a physical link here. It's a 40G link, but it doesn't really matter right now how fast that link is. And we got a simple flow table, which is here. The first 2 flow rules is just a simple flow rules to provide connection between the victim's machine. So as you can see that it's allowing the proper IP addresses of the victim's machine here. And now we have here the 2 attacking but still benign ACR rule. One is matching on port 80, and the other one is matching on the source IP. Of course, we are matching in the destination IP at the moment to figure out the proper way, but it doesn't really matter at the moment. So this is the 2 header fields that we have masks and wildcards. And now I'm going to show you how this thing works in reality. So we have an online Grafana for plotting the results. So what you can see here at the moment that we have 3 plots. The plot on the top is just the current CPU load. It doesn't really say too much at the moment. It's around normal operation. Those servers, there's actually nothing, just hosting these virtual machines. On the second plot, we will see how the OpenVSwitch megaflow cache entries are increasing during the process. Now it has just a couple of megaflow cache entries because some ARP packets are there, and then the hosts try to communicate. And on the bottom, we will see the OpenVSwitch performance, which I will start. So I start on I will start an in-house development of Berkeley Lab's hyperv. It's just some bullshit on the back, but it's don't. And now I try to connect from a client. And what you can see here, that if I switch back to the Grafana, we will see that this is the average throughput that now we can achieve between those two virtual machines and its first servers. So it's around 8 and 9-ish gigabit per sec at the moment. And since there are just one flow between the two virtual machines, the number of megaflow cache entries increased only just with a couple of numbers. So it's like it is now 4 and 3. So the number of flows is 4 and the number of masks is 3 at the moment. But if I since I'm going to be an attacker and I know how the flow table look like, and accordingly I will generate some traffic sequence to show how this attack can be carried on. So it's another script. Just a sec. So now I'm going to only attack on port 80 at the moment, and what you can see here, you can see nothing here. Okay. Then I just started. So now I send 1,000 packets per sec into the system, which is not really a huge number, and so it's not possible to. Okay, I try to. What if I do this? Okay, it's much better. So what you can see here, that the number of megaflow cache entries just increased from 2 or 3 to 20 with the 16. So now we are attacking on 16 bits. Now we are attacking on the TCP destination port. So we got 16 bits. If I know the flow rule and I know how to generate packets, I can actually reach that the megaflow cache and the number of megaflow cache entries will be 16 or 17. And of course, it's a bit higher because of the hyperv victim traffic in the background. And what we see that the attacker rate is really unrecognizable. Actually, it's just a couple of hundreds of kilobits per sec, and the victim rate just dropped down to the half of it. So it became 4.6-ish gigabit per sec. And if I also try to attack on another IP header, which will be the IP source address, then you will see that the effect of the cross-product problem so you can see that the attack was here stopped. The OpenVSwitch Megaflow cache has a 10 seconds of timeout. So this is the reason why the victim's traffic was also bad at that time. And you can see that it almost tried to go back after 10 seconds, but now I started the attack again, and the performance of the victim actually dropped down to 0, like a couple of hundreds of megabit per sec from the 9 gigabit per sec. So even if it's not a complete denial of service at the moment, but we can also introduce some new header fields and some new packet sequence, it's a really huge degradation of service. And it is really difficult to recognize this from an operator's point of view, because we're not generating a huge amount of packets into the system. So if I go back, okay, so yeah, these were just fallback slides if the demonstration is not working. But we have seen here that as we introduce the new header fields and new attacks, then the performance can be dropped down. And I guess I also have a, if I introduce the third TCP source port that I didn't show at the demo this time, then it cannot be realized from this scale, but it also went up from 520 megaflow cache entries to thousands of it. So it's really interesting that even just a couple of hundreds of entries in the megaflow cache can actually result OpenVSwitch to perform really bad. And we also try to analyze these effects in a broader scale. So we looked for what are the deployments that are using OpenVSwitch at the moment, and we focused in the beginning only on the public cloud deployments. And we found out that there are several public cloud deployments which replace their inner networking module to OpenVSwitch to avoid several layers of networking, which is provided by the Linux kernel, and several layers of virtualization. So if you use OpenVSwitch, then it probably should be faster. So this is how the OpenVSwitch guys are selling their ideas. And we could also carry out these attacks. So this is a Kubernetes example. So Kubernetes by default uses IP tables for implementing the ACR rules, but there is an alternative called Kubernetes OpenV. Is this the Open Virtual Network? So
yeah.
that's the management based on OpenVSwitch, and this is what the OpenVSwitch guys are developing. And what we also achieved, so in this setting, the main throughput wasn't that big in the beginning, but it was 1 gigabit per sec. And as we, at the 60th second, we initiated our attack in the same way as we did before in our synthetic setup. And we also see this degradation of service. And what we also see is that in OpenStack environment, this whole attack can also be carried out. But now we are in this plot, we have a slightly different setup, because what we realized that in OpenStack environment, the attack can only carry it out if there is no background traffic in the beginning, right? Am I remembering it right? So it can only be there if there are existing flow rules. So if there are no flows in the cache, and then we start the attack, and the victim just step into the system after the attack already launched, then for some undisclosed reasons, we don't know that at the moment, the attack is not working. So somehow OpenVSwitch tries to prioritize something in their inner structure, or some other tricky stuffs are in the heuristics. So what we can see here that when the attack is on and a new flow is coming in, then it is working. So this is a case when it is working. So you can see that the victim's traffic is not really high, it's just a couple of hundreds of megabits per sec. But when we stop the attack at the 60th second, and the victim is still having the hyperv throughput measurement, it just goes up to its peak for 1.4 gigabit per sec. And what we can see here that even if you restart the attack at the 90th second, then it doesn't have any effect to the already going traffic measurement. So it's this is just the end of the measurement. So don't really consider the right part of the plot. So in OpenStack, it just works a little bit different. And if we are talking about possible attacks, we also need to consider, of course, some possible mitigation techniques. So what are the immediate actions that we can actually carry out to handle the attack? So we can increase the number of CPU cores available to OpenVSwitch. So yeah, if you have a really big bare metal stuff with hundreds of cores, then this is not really a problem to just search sequentially the 500 megaflow cache entries. But if you have just one core, a regular Intel Xeon processor, then it can really be bad, as we saw before. We can also disable the megaflow cache processing in OpenVSwitch completely, but of course then we are actually attacking ourselves, because that's a really important part of the fastpass. So if you disable some part of the fastpass, it will introduce some slower overall performance, but at least this kind of problem can be avoided. And we can also offload the ACR processing from OpenVSwitch to IP tables. This can be switched on in some settings, in these public cloud deployments, for instance. And we can also offload OpenVSwitch itself on a SmartNIC. And if you use jumbo frames, for instance, instead of the 1500 MTU sizes, then we can also drastically reduce the per packet load. So now we saw the throughput in gigabits per sec, but actually it's always limited by the per packet load. So if the packets are bigger, of course, then the throughput will be bigger with the same amount of with the same number of packets. And of course, we can use our monitoring tool that I just showed to spot how these megaflow cache entries are increasing. And of course, if they are like, if it's above 500, then we can alert the operator, or we can carry out some further investigation that what is going on in our network. And of course, we are also open some new ideas how you might find it and how you can mitigate the attack. So yeah, so that would be our short introduction of our work. Thank you. And I don't know whether these are just further backup slides. So yeah, so thank you. If there is any question, I guess there should be, because I was fast and maybe that was a bit complicated from the first side. Yeah, thank you.